So let's proceed now. Case 1. Case 1. What is it? When the driving frequency and this is natural frequency, this is driving frequency. So case 1 is for low driving frequency. For low driving frequency, that means when omega is much less than omega naught. What do we observe? When omega is much less than omega naught, the driving force frequency is much less than the frequency of oscillation. Well, then the displacement amplitude, if I just move a little bit up, then you can see the displacement amplitude. This, when omega goes to 0, because it's much less, when omega is going to 0, then it can be neglected compared to omega 0 square, the natural frequency. So for k square omega square, can be neglected as compared to omega 0 square whole square. Okay, so what we write over here, when omega goes to 0, the amplitude A will be equal to f0 by omega 0 square. Okay, what is f0? We have seen just now, it is f0 by m. And what is omega 0 square? It is s by m, isn't it? It is s by m. So this is equal to f0 by s. Thus, at very low driving frequencies, the amplitude of forced oscillation, okay, it depends upon the driving force F0 and the stiffness constant S, but it is independent of frequency. It is just independent of frequency. When you make the driving force frequency very low, it is independent of both omega 0 and omega. Of course, it is dependent on omega 0, sorry, but it is independent of the frequency of the driving force. It just depends on the amplitude of the driving force F0 and the stiffness constant of the medium. Now suppose you go to case 2. Case 2. What is case 2? Well, case 2 is when omega is much greater than omega naught at high driving frequency. So this means high driving frequency. High driving frequency. What is it that we observe when the frequency is very high? Now again, if you take the same value for the amplitude A, what was it? It is equal to F0. This should be at the tip of your finger. Square root of, ultimately, this is what you have to, when you try to explain these portions, you have to start from here. So you don't have to sit and do all derivations from before. So try to arrive at this relation and keep it at the tip of your finger when you try to explain this part, because this might come in your exam. Omega square minus omega 0 square whole square. So you see, this is equal to, you can write this as equal to what? At high driving frequency, this is equal to f0 square root of, yes, 4 k square omega square. Now then you can neglect omega naught because you are making this very high. So plus omega to the power of 4. This is what you will be getting. Okay, so you see, if the damping constant is very small, so that 4 square, suppose say we make for small k. Now this you can write as f0 by omega square. Here, if you make your damping constant very small, this happens for very low. This is very important, otherwise you won't get it. For very low damping constant, for very low damping constant, this will happen. Okay, so for very low damping constant, this is what you will be getting at high driving frequency. Okay, then as omega tends to infinity, you make the frequency infinitely large, this is amplitude, this is the expression for amplitude if you remember. So then what happens to the amplitude? If omega tends to infinity, so for omega going to infinity, amplitude goes to 0. That is, the amplitude almost approaches 0 as the driving force frequency becomes very large. Okay, so let us move to the last case, the case where you get your short note, and it is very important, and that is why I am saying this is the case where you have to be very careful. Okay, well, what is it? Well, the case when omega, that means at frequency of displacement resonance. Okay, so case 3, you call it amplitude resonance, so you get short note on that in forced vibration when omega is equal to omega naught. Okay, then the driving force frequency is equal to the natural frequency of the oscillator, so we call this case the case of amplitude resonance. Okay, so just simply then you will get, if you just substitute omega equal to omega naught, you will just get f naught by 2k omega. Thus, at a driving force frequency equal to the resonant frequency, the maximum amplitude is inversely proportional to the damping constant k. For small damping, amplitude is large. For large damping, amplitude is 0. Theoretically, when damping is 0, this is infinite. Okay, so this is called the case of amplitude resonance. So, however, if you consider it mathematically, so this little thing, if you write, you won't get much marks. You have to show this mathematically. Okay, if we just consider the case when the damping is present, then the displacement resonance or the amplitude resonance, at what frequency when the damping is present will the amplitude resonance take place? Suppose we try to find out the frequency. Okay, how will we do that? Well, we will write, see, A is equal to f naught by square root of 4k square omega square plus omega square minus omega 0 square whole square. Okay, so when, at what frequency will we get the amplitude resonance? Okay, suppose when the damping is small, when the damping is not equal to 0, what should we do? To find the frequency, we must do dA d omega equal to 0. If we do that over here, you will see that the corresponding frequency at which this happens, I'm not going to do it, you are going to do it, because if I do it, this video will take a long time. That simple differentiation, if you do, you will see that for omega square equal to omega 0 square minus 2k square, well, this happens. Okay, that means at omega equal to square root of omega 0 square minus 2k square, the damping amplitude, displacement amplitude A is maximum. Okay, so this, if you substitute, you can show, if you take out omega naught from this equation, so that you get omega 0 square in the denominator here, you can show that this is equal to, well, omega 0 square root of 1 minus 2k square by omega 0 square. Okay, which further simplification, why it is necessary in case you get problems. Okay, square root of 1 minus r square by 2m square omega 0 square. Okay, so thus the maximum displacement amplitude, if you plot, or the displacement resonance, takes place at a frequency slightly less than the natural frequency of oscillator, and it is given by this. Okay, so the resonant frequency of driving force omega is slightly less than the natural frequency of displacement omega 0. It's slightly less when resonance takes place. What resonance? the amplitude resonance. So suppose we plot a graph like this for amplitude resonance. What do we get? See, this is your displacement amplitude. If you write displacement amplitude, your displacement amplitude A, this is your displacement amplitude A, and this is, suppose you write omega, then for amplitude resonance, this is how you get your graph. You will see it in all books. Okay, it goes like this, where you have your maxima here, and then again for various values of k, you will see this happens. It goes like this. Okay, so these are the various values of the damping constant R2, R1 less the damping constant. So here R1 is greater than R2. The less the damping constant, the higher is the peak, such that when the damping constant goes to 0, you get the whole amplitude goes to infinity. Okay, so well, here is your omega naught. So this is something which you have to show, prove and discuss if you are given short note and on amplitude resonance or displacement resonance, which comes very often in forced vibration.